I'd like to welcome all of you and thank you for attending. This is an introductory webinar on thermomechanical analysis for beginners. So my name is Pamela Shapiro, and I am a thermal application scientist. My focus is in polymers, and I work at Netsch Instruments North America, located in Burlington, Massachusetts. These slides that I'll be presenting to you today were assembled by Doreen Rapp, who's the application scientist specializing in dilatometry and thermomechanical analysis at Netsch headquarters located in South Germany. So this is an outline of the presentation, and I will first go through some basics about TMA measurements with definition, a list of standards, a description of the measurement principle, the kind of results one obtains in these measurements, and the sorts of applications that TMA is important to. Then I will give you a wide range of application examples to show you the utility of this thermomechanical measurement method, and I'll follow that with a summary and a question and answer session. So shown in this definition here, thermomechanical analysis is a method that measures the changes in sample length or volume as a function of temperature or time under a controlled temperature program, a specified atmosphere, and a non-oscillatory load. Now, the load on the substance can be compressive, tensile, flexural, or torsional nature. And when the applied load is very low, the TMA is used to measure changes in the dimensions of the substance. And actually, under those circumstances of a negligible load, the measurement is called thermodilatometry. And oftentimes, these two terms are used, albeit incorrectly, interchangeably. There are a variety of standards that describe the proper approach to performing measurements on a variety of materials by thermomechanical analysis. A few of these are listed here. Most of these, most commonly, the TMA measurements are used to measure the coefficient of thermal expansion of materials, as well as glass transition temperatures. And there are also some special measurement modes, and you will see some of these a little bit later on in the presentation. In the measurement, the basic measurement principle, you apply a programmed force to the sample shown here and measure dimensional changes to the sample under the load during a programmed heating or cooling of the sample in a furnace. So that's represented by these temperature arrows. Measurements can also be performed isothermally. And this is a diagram here showing the basic features of the instrument. The sample is easily inserted between the push rod and the sample stage, or sample holder. And the sample holders and push rods are fabricated from either fused silica for measurement at temperatures up to 1100 degrees Celsius, or from alumina for measurements above 1100 Celsius. Now, an electronic force control through this actuator shown here, allows the force on the sample to be set to as low as 1 millinewton and as high as 3 newtons. And a highly sensitive force sensor continuously senses the force that's applied to the push rod and readjusts it automatically. There are 4 different standard measurement modes available depending on the shape, thickness, and strength of the sample, and these include compression, shown in this figure, penetration, shown here where there's a little sharp piece coming out of the compression rod, and tension is shown here for films, and then you have 3-point bending shown here. Now what is measured is the change in the length of the specimen as a function of time or temperature. This is typically plotted as a curve that shows the change in one dimension of the sample, or as shown in this equation, the change in the dimension of the sample relative to its initial magnitude. And from this thermal expansion curve, one can derive the expansion coefficient. There are generally 2 different coefficients that have been defined, and the average expansion coefficient is the one that's most commonly reported. It refers to the expansion sample length change, delta N, over a particular temperature interval, delta T, relative to an initial sample length, L naught, that was measured at a reference temperature. That's often ambient temperature, but it can be a different temperature as long as it's specified. So this is generally used for cases where the expansion occurs relatively at a relatively continuous rate. The physical expansion coefficient is actually the derivative of the thermal expansion curve. It's the instantaneous slope at each point in the curve, and the equation for that is shown below. And both of these types of expansion coefficients are directly calculated by the software provided with the instrument. TMA is applied to a variety of materials, ceramics and glasses and glazes, including the raw materials, the raw clay, for example. It can be applied to metals and a variety of inorganic materials, and it's commonly applied to polymers as well. And it can be used on materials in various phases, solid pieces, powders, and pastes, as well as liquids, fibers, and films. This list here shows the various types of information you can obtain from the TMA measurements. Things like we've already described the linear thermal expansion of the material, the coefficient of thermal expansion. The curves also indicate phase transitions, the temperatures at which those occur, the temperature at which sintering occurs, things like transitions such as glass transitions, softening points, as well as decomposition temperatures and density changes. And you can also derive some kinetic data from the measurements using some additional software that is offered. So now I will show you a variety of application examples that show you the value of of TMA in materials characterization. Before I show those applications, I just want to show you the instrument on which the measurements were performed. This is the Netsch Hyperion TMA, and what you see here is that the instrument houses two easily exchangeable furnaces, a steel furnace that can be cooled to as low as minus 150 Celsius and heated to as high as 1,000 degrees Celsius. And for higher temperatures, we have the silicon carbide furnace, which can be operated from room temperature up to 1,500 degrees Celsius. The instrument can accommodate a sample length up to 30 millimeters and can measure dimensional changes up to 2.5 millimeters with a resolution of 0.125 nanometers. And it can exert a force anywhere from 1 millinewton to 3 newtons with a digital force resolution of less than 0.01 millinewton. And then I already mentioned the temperature range available depending on the furnace that you employ. So here's an example that illustrates why it's important to know the thermal expansion behavior of a material. It's a measurement, it's a standard expansion measurement on steel, which exhibited a fairly linear expansion between 40 and 740 degrees Celsius before undergoing a phase change, and you can see that here, to a new crystalline form that is more compact. And that form also continued along a similar trajectory with continued heating. Now this curve, that's the thermal expansion curve in blue. This red curve is called the technical alpha curve. And if you recall my description of the average expansion coefficient, this measures the coefficient by comparing the expansion relative to a reference temperature. In this case, the reference temperature, the length of the sample at 40 degrees was taken as the reference, and calculates it throughout the curve. If you notice the expansion coefficient, the average expansion coefficient here varies from 10 to 15 times 10 to the minus 6 per degree. That's an important parameter because there's a variety of materials that are constructed out of steel, such as railways and bridges, and these structures can encounter large temperature ranges, large temperature changes between summer and winter, particularly here in the northeast of the United States. So if we take the coefficient of the average coefficient of expansion, let's take it as the lower value of 10 times 10 to the minus 6, and we apply that to a 1 meter piece of steel over a 10 to 30 degree temperature range, or a temperature change of a 10 to 30, rather a 10 degrees C to 30 degrees C, which for those of you in the U.S., that's a change of 14 Fahrenheit to 86 Fahrenheit, and that's entirely reasonable expectation for us here in the Northeast. That 1 meter of steel can expand by as much as 40 centimeters, and that can produce some significant warping and failure. And this is the reason why expansion joints are included in bridges and small gaps are typically included between the rails of jointed tracks. And there are now tracks that are fully welded, but still people have to keep an eye on them to make sure 40, oh no, I'm sorry, not 40 centimeters, it's 4 centimeters. Still a substantial amount. Okay, so here's another example involving rubber. It shows an expansion measurement in which the rubber passes through a glass transition at minus 62 degrees. The glass transition is a reversible transition in which the amorphous polymers go from a hard, brittle, glassy state at the lower temperature to a soft, rubbery, more expansive state at beyond their glass transition. So here again is the thermomechanical measurement, and what's been plotted along with it is the DSC measurement. You can see with the Proteus software you can plot two different types of measurements simultaneously, and in a DSC measurement the glass transition looks like a step in the curve, and the glass transition temperature is taken from the midpoint of that step, and as you can see it's at minus 62 in agreement with the measurement obtained by TMA. And now here's another polymer measurement, and it's called a creep measurement. It's on an O-ring, and it's measuring the extent to which the elastic properties of a seal, an O-ring seal, remain intact over a constant load. And this is very important in determining how well the seal, the O-ring can maintain its seal. So this is a creep recovery measurement again. And in the first part of the measurement, the creep response of the O-ring is measured under a load of 3 newtons over 40 hours. And as you can see, a maximum compression of 21% relative to the initial thickness of the seal was measured. Then the force was relieved to only 5 millinewton, after which the majority of the strain, okay, the stress is the load, the strain is the deformation, all but about 4% of the strain was reversed in the first hour. But note that here, after 30 hours, the return from deformation was only 19.2%. So the sample did not return entirely to its original thickness after 30 hours. And this is due to the tendency of the polymer to flow under stress. Another way of measuring this type of behavior is called temperature retraction. This is a common test that's applied in the rubber industry, and it's actually considered a useful indicator of a material's low temperature performance. And the TR10 value describes the temperature at which a stretched or compressed sample reaches a recovery of 10% after freezing. So the TR10 value is the conservative value for the lowest temperature at which that particular seal can be used. This is the type of measurement program that I'm going to show on the next slide. You first have a compression of the sample at room temperature before cooling it down below the expected TR10 temperature, before decreasing the sample load and allowing the sample to warm back to room temperature in order to determine at which temperature it recovers by 10% of its deformation. So here's the Here are the various curves. There's the thermal expansion curve, here's the force curve, and here's the temperature curve. And as I show, we have a force of applied. In this case, it looks like it's 0.2 newtons that's applied to the sample at room temperature, compressing the material, and then once the material is compressed, the temperature here of the sample is lowered, and you can see from the right-hand axis here, this temperature axis, that it's cooled down to minus 100 Celsius. During cooling, the force on the sample is relieved, and then the sample is heated back up to room temperature, and the thermal expansion of the material is monitored while it's heating back up. And you can see here again, there's that glass transition. So it's strained and distorted, and then it's allowed, that distortion is relieved. And what we're interested in is the temperature at which that distortion is relieved by 10%, and that's a point measured from an extrapolated line from the linear expansion from the point below the glass transition. That's measured from the curve to that point. And these types of measurements are performed automatically by the software. There's a program in the Netch software that does those measurements, performs those measurements for you directly. And it can give you the TR10 value as well as the value for 20% recovery and 30% recovery. Someone's asked for the PowerPoints after the webinar, and I'll show you a website, URL for the Netch website where you can download a PDF format of the PowerPoint slides. This slide here shows measurement on PVC, polyvinyl chloride, according to an ASTM method, E2769, for measuring the Young's modulus of the material, the elastic, which is the elastic modulus. And what it shows you is measurement with the TMA. You can sweep through a linear force range and monitor the change in the dimension, one of the dimensions of the sample with the increasing load. And what this plot shows you is that there's very good agreement between two separate measurements on the PVC sample. In fact, if you compare the values for the Young modulus obtained at half a Newton, see here 2,883 megapascals and 2,856 megapascals, they differ by less than 1%. Besides stress sweep measurements, one can also perform what are called strain sweep measurements, where you sweep through a range of deformations of the sample and record the amount of stress applied in order to achieve those deformations. That's known as a stress strain curve. And again, here you can see there's a red curve and a black curve on the material showing the high reproducibility of the measurements. This slide shows a measurement on a carbon reinforced polymer, and the high strength and lightness of carbon reinforced polymers has made them very valuable as structural materials for vehicles, including aircraft. Because of the polymer, the polymer is very lightweight, but the carbon gives it strength that's comparable to that of steel. And as with the steel example shown earlier, one is concerned with the effects of temperature on the structural integrity of the material. Now, these carbon reinforced polymers are generally anisotropic, so the carbon fiber is aligned in a particular direction, and so their thermal expansion differs perpendicular to the fiber direction as opposed to parallel to the fiber direction. This measurement shown here is perpendicular to the fiber direction, and you can see that the expansion here there's a change in the rate of expansion, which probably corresponds. It's got an onset temperature of 127 degrees C for that change, and that probably corresponds to a glass transition in the polymer. So here, in this case, perpendicular to the fiber, the thermal expansion behavior of the material is dominated by the polymer. And what you can see in red is the technical alpha curve showing the average coefficient of thermal expansion and how that changes as you proceed past the glass transition temperature. Here again is that measurement, but in addition we have the measurement now in the direction of the fiber, and what you can see here now is that in that direction the carbon is restricting the degree of expansion of the material as a function of temperature. In fact, there's essentially no expansion in that direction over the entire temperature range measured here from minus 50 to 150 Celsius. Okay, in the next slide I'm going to show you another application that's possible with the TMA. The TMA can be operated just to a limited degree like a DMA, dynamic mechanical analyzer, so you can modulate the force instead of providing a constant or linearly increasing force. You can oscillate the force between a certain target amplitude to a minimal amplitude. And in this measurement, I'll be showing you, we measured the viscoelastic properties of this piece of polytetrafluoroethylene of 1 millimeter thickness and 5 millimeter width, and it was measured on a 3-point bending stage with a bending distance of 20 millimeter. Now the force imposed by this push rod here was modulated at a frequency of 0.2 hertz. Now what differs between the TMA and the DMA is that in order to accommodate the changing stiffness of the sample over the temperature range of the measurement, multiple segments had to be programmed in order, and each segment had different force amplitudes to minimize or to control the amplitude of the deformation as the sample softened. This just mentions that for an exact evaluation, you generally do a baseline measurement or correction run with an infinitely stiff reference sample, such as a thick aluminum block, and that's subtracted out. That's to subtract out the effects of the holder itself from the measurement results. So here are the results of the measurements. As you can see, there's 3 different segments here, each involving a different force. The first segment involved a force of 1.8 newtons, the second 1.2 newtons, and finally 0.6 newtons as the material softened towards its glass transition. This envelope here, actually, it looks like a ribbon here, shows the dimension of the sample, but it's actually this curve here envelops an oscillating change due to the frequency modulation of the applied load. And what you can derive from this curve is what's called the storage modulus, E prime. This is the elastic modulus of the material. And it's basically the ability of the material to store energy, and this becomes reduces as the material undergoes transitions. So as you can see here, this first reduction here, this first transition, indicated by the change in the slope of this E prime curve in red, is a phase transition. That's referred to as a beta transition. And you can't really see here, it's kind of blocked by this box, but right over here, you also have a solid phase, crystalline phase transition, and a couple of them, in fact. And down around here, and it's not easy to see, you have a glass transition around 125 degrees. Now you can also plot this with a log plot, and that kind of amplifies the appearance of these different transitions. So this illustrates how you can use TMA in a kind of DMA mode to characterize viscoelastic properties. Viscoelastic meaning that the polymer is behaving both like a solid as well as a liquid. Although it's elastic, it returns back to part of its initial shape, or returns the force or the energy that's imposed on it. It also flows to some degree. And here's another example showing what one can gain by being able to apply an oscillating force to the sample. In some polymers, the glass transition is extremely weak and very difficult to see, even by differential scanning calorimetry, for example. And so if you apply, as it's done in this case, a modulated force, and in this case it was a square wave instead of a sinusoidal modulation, with a static force of 0.25 Newton and a dynamic force, oscillating dynamic force of 0.25 Newton at a frequency of 0.2 hertz. You can see the glass transition a little more clearly. You can see here the average thermal expansion curve along with the modulating curve about it, and what you can see is that the width of the modulations increase as you pass through that transition, making the glass transition clearer. And here's an example of the casting of molten metal, and shows you where TMA comes in. So in order to optimize a casting process, one needs to obtain information about the thermal properties of the metal being casted. And a particularly important parameter is the heat conductivity of the metal, and that's represented by this lambda here, thermal conductivity, which is dependent on the temperature-dependent density of the metal, the specific heat of the metal, and a parameter called the thermal diffusivity. Now, the specific heat can be measured over a range of temperatures using a thermal analysis method called differential scanning calorimetry. And the thermal diffusivity of the material can be measured using a method called laser flash analysis, and instruments that accomplish these measurements are also offered by NETCH. But the bulk density, as a function of temperature, is measured with either dilatometry or thermomechanical analysis. Here we see the thermal expansion curve of the of cast iron, which is a ferrous alloy, and it's been heated until it liquefies, and then once it liquefies, it's poured into a mold to solidify. So this plot simulates that expansion behavior during the casting process. And what you can see is a nearly constant expansion until the melting temperature of the material at around 1,333 degrees C, at which point there's a large increase in the expansion of the material until it is completely molten at around 1,371 degrees Celsius. Here's the technical alpha curve showing the average coefficient, average expansion coefficient, and how it increases dramatically at the melting onset. Now, the software, the analysis software module has a density determination module, which allows you to take this data and, assuming an isotropic material, it calculates for you the density of the material as a function of temperature. And from that, you can then use that density in your thermal conductivity calculation. And this is an example of molding sand, which is principally used for making molds for metal casting. There's a sample on the left before heating, and this is after heating, and you can see that it's changed color somewhat, and that's due to the oxidation of iron 2 present in the sample to iron 3. This measurement, as you can see, was performed in air. One thing I didn't mention here is that the thermal analysis measurements are typically performed at a fairly low heating rate. If you're familiar with DSC, for example, heating rates as high as, very high heating rates can be used, but typical heating rates for DSC are 10 to 20 degrees per minute. With TMA, it's generally on the order of 2 to 3 Kelvin per minute, sometimes 5 Kelvin per minute, in order to make sure that the sample is completely equilibrated in temperature, the entire sample, throughout the sample over the while you're scanning through the temperature range. So these measurements are typically performed at a lower heating rate. This heating rate here, it was performed at 5 K per minute. Okay, carrying on here. So what we see here is the expansion of the material. There's what appears to be a phase change here. It's unidentified. I'm not sure what it is. It could be associated with the oxidation of the iron from iron 2 to iron 3. And then there is a substantial change here with an onset temperature of 574 degrees Celsius. And this is due to an alpha-beta transition of the quartz in the clay. And this curve here, again, this is I believe this is actually not the technical alpha curve. This is actually the first derivative of this curve. So this is the physical alpha. And it kind of shows that the change in rate of expansion peaks at 578 degrees Celsius. This shows a measurement on a powder sample. So I mentioned in an earlier slide that you can perform measurements on solids, pastes, liquids, powders. Here's a measurement involving nickel alumina powder. And the way this is done is you put the powder in a typical crucible that's used for, this is an aluminum crucible. It's used, for example, for thermogravimetric analysis measurements, and this is a disc. You put the disc on top of the packed powder, and then you use your push rod on the disc. You can measure the expansion that way. And this shows two different heatings, and there appears to be some irreversible change in the material happening after the first heating that's not apparent in the second heating that's represented by the red curve. In this case, the heating rate for this sample was at 3 Kelvin per minute. This was done under a nitrogen atmosphere with a constant force of 0.25 newtons. So here's an example of a sintering reaction of aluminum titanate, and the black curve is the thermal expansion curve. The dash curve shown here is actually the first derivative, which is showing the rate of thermal expansion. So a variety of things happen during sintering, including a binder burnout before the sintering phase, and the rate at which this type of process occurs can affect the quality of the final product. And it's possible by modifying the temperature program, if you know the rate at which these processes occur, you can modify the product of the process, the heating rates, for example, so that rather than a continuous heating rate shown by this red curve, you modify it in order to control the rate at which those different processes occur. You can optimize things like densification and grain size distribution. So in order to do this, you need to do a kinetic modeling of the thermal expansion curve, which means this requires a kinetics program, and you need at least 3 measurements, 3 different heating rates, followed by the kinetic analysis. NETCH does offer a kinetic analysis program for this purpose, and using the results from that kinetic analysis, you can then have the software actually program a rate-controlled sintering process, and that's shown in red here. So this blue curve, this blue thermal expansion curve, is without rate-controlled sintering, and this red curve with a more gradual change in the dimension of the sample is with this rate-controlled applied sintering program applied. Here's an interesting one showing the effect of not heat but humidity. So this is an isothermal measurement at 35 degrees. The force, this was done in tension mode, and a very, very small force of 2 millinewtons was applied, and the humidity level the relative humidity was changed in a stepwise fashion, as you can see from the red curve here. It was decreased from 60 to 30% relative humidity in 10% steps, and what you can see is a decrease in the length of the hair with a decrease in the relative humidity. And I figured this has to be straight hair, because we all know that curly hair actually decreases or curls up in the presence of water. So in this case, we have a shortening with the decrease of water in the atmosphere. Now, the purpose of this measurement here, the analysis of this clay, is to show you a measurement, a TMA measurement coupled to mass spectrometry, a mass spectrometer. So the Hyperion TMA is gas type. And the advantage of that is that you can couple the furnaces to evolved gas analyzers such as a mass spectrometer or an FTIR in order to analyze the gases that are evolved from a sample during heating and compare the evolution of those different gases with the changes in the phase changes or the dimensional changes in the sample. So here the thermal expansion curve is shown in green, and it's marked by some variety of transitions here. These curves here show the mass ion signals from the mass spectrometer for mass ion 18 and 4418 is the ion ratio for water, mass ion ratio, the mass to ion ratio for water, and 44 is for carbon dioxide. This measurement was done under air, so there's clearly some organic material that burns off between 300 and 500 degrees Celsius. And there are also peaks showing the evolution of water at various times during the measurement. And I noticed that a sudden contraction in the material dimension occurs at a point where there's a large spike, a large evolution of water. TMA is used to measure softening points in materials. Shown here, this is a measurement on glass. You can see here that the glass undergoes a glass transition at 739 degrees C, followed by a softening point at 799 degrees C. And it's used to measure refractory materials. So if you say you're measuring refractory materials, here's an example of trimedite theta. These are used as linings for furnaces, and the lifespan and efficiency of any furnace can be improved by operating it within the limitations of its lining. And thermal expansion is an important criterion for assessing the behavior of these materials under thermal stress. So what you see here are multiple transitions. Here, the alpha-beta transition of the trimedite. Sorry, it's I call it tridentite. It's tridemite, and then you see here is an alpha to beta transition for quartz. Another unidentified transition at 1,233 degrees Celsius, and finally a softening of the material at 1,450 degrees Celsius. So this measurement shows the thermal behavior of a typical coarse-grained refractory material, and that can be accommodated by the TMA, which has a size limit of 30 millimeters. All right, so that's the end of the application examples. A summary of the applications for TMA: material development, quality control, failure analysis, and process development. So the kinds of information that are gained through TMA analysis are things like thermal expansion, coefficient of thermal expansion, transition temperatures, sintering information, softening points, and as I said, this technique can be applied to a variety of materials and in a variety of formats: solid, powder, pastes, fibers, films, and liquids. And I've also discussed some, besides the TMA, Hyperion 402, which has two models, the F1 and the F3, The instrument can be coupled to FTIR, a mass spectrometer, or a humidity generator if you'd like to explore the effects of humidity on the dimensional properties of your sample. And I'd like to thank you again. My name is Pamela Shapiro. This is my email here. Doreen Rapp is the TMA expert at the NETCH headquarters, and shown here is her email, and additional questions can also be directed to ngb_webinar@netch.com.